Hello, this video covers Lewis structures. When we talk about a Lewis structure, it contains the elemental symbol surrounded by one dot for each valence electron. So if we were to look at the elements that are in the third period on the periodic table, starting with sodium, sodium has the electron configuration neon 3s1. That means that a sodium atom has one valence electron. If we want to draw the Lewis structure for sodium, we would have our symbol Na and we would have one dot. And again, that dot represents the one valence electron that an atom of sodium has. If we were to look at magnesium, it has an electron configuration neon 3s2. So magnesium has two valence electrons. Its dot diagram would have two dots. Moving on, aluminum is neon 3s23p1. It has three electrons in the third energy level. So there are three valence electrons. We would have three dots. And going down to argon, argon is neon 3s23p6. It has a total of 8 valence electrons. Its Lewis structure would have 8 dots. Now, if we were to look at Lewis symbols in molecules, we're going to have two types of electrons. We're going to have what are called bonding pairs of electrons, which are electrons that are being shared between atoms. And we have lone pairs of electrons, which are not being shared in bonding. Now, we can have more than two electrons being shared between atoms in a bond. If we look at single bonds contain two electrons being shared between atoms, and we would designate it with a single line. So this represents a pair of electrons being shared between nitrogen and hydrogen, or a pair of electrons being shared between oxygen and hydrogen, or a pair of electrons being shared between hydrogen and fluorine. Now, for double bonds, we have a sharing of 4 electrons, or 2 pairs of electrons. So we have a double bond here between oxygen and carbon. It's 2 pairs of electrons, or a total of 4 electrons being shared between carbon and oxygen. And a triple bond is where we've got 3 pairs of electrons, or 6 total electrons being shared between atoms. So this would represent a triple bond between carbon and oxygen. So when we look at Lewis symbols, they're going to enable us to show several different things. One of the things we can see is ionization reactions. So if we were to look at sodium, sodium has one valence electron. And when that sodium atom loses an electron to form a sodium positive ion or a cation, and we lose an electron, we would lose that one dot. If we were to look at calcium, calcium has two valence electrons. And when the atom becomes a calcium cation, it loses those two electrons, so the two dots on the Lewis structure are removed. Now, let's say we have chlorine. Chlorine has 7 valence electrons. If it were to gain an electron, then it forms an ion with 8 valence electrons. Or if we had a sulfur atom, which has 6 valence electrons, and it gains 2 valence electrons, now we've got a sulfide ion that has 8 valence electrons. So these Lewis symbols can help us to show ionization energies. They can also help us to show electron transfers between ionic compounds. So let's say that we've got magnesium, which has 2 valence electrons, and oxygen that has 6 valence electrons. If the magnesium transfers its electrons to oxygen, we would end up with a magnesium ion with a +2 charge because it lost 2 electrons, and an oxide ion that has a -2 charge because it gained 2 electrons. Or if we have a calcium atom, which has 2 valence electrons, and a fluorine atom that has 7 valence electrons, each fluorine would gain 1 electron from calcium. So we need 2 fluorine atoms. And then we'd end up with a calcium ion that has lost 2 electrons and 2 fluorine atoms that have each gained 1 electron to form a fluoride ion in order to form this ionic compound. Now, when we talk about drawing these Lewis structures, we want to go through a step-by-step process. The first step is going to be to determine the total number of valence electrons that are in the structure. How do we do that? For the main group elements on the periodic table, that would be the alkali metals, the alkaline earth metals, the elements that are in the nitrogen group or the oxygen group or the halogens or the noble gases, the group number designates the number of valence electrons. So the alkali metals all have 1 valence electron. The alkaline earth metals all have 2 valence electrons. The nitrogen group has 3 valence electrons, or 5 valence electrons. Oxygen has 6 valence electrons. The halogen group has 7 valence electrons, and the noble gases, with the exception of helium, have 8 valence electrons. Now, if we're talking about ions, ions have charges. If we're looking at positive ions, we would subtract an electron for each positive charge. And if we look at negative ions, we would add electrons for each negative charge. Once we've determined the total number of valence electrons, the next thing would be to draw our skeletal structure. And the way we would do that is by determining what the central atom is. That's usually the most electronegative element in the particular compound, placed in the center. And then we would put the other atoms around that central atom. We would connect each atom to the central atom with a single bond, which again is a pair of electrons. Then we would add in all of the remaining electrons as lone pairs of electrons on the terminal atoms, with the exception of hydrogen, because hydrogen won't have lone pairs of electrons. And we would do that until we complete the octet. In other words, all of the terminal atoms, with the exception of hydrogen, would have 8 valence electrons in the structure. Now, if there are any remaining electrons, we would add them to the central atom. Once we've added all of our electrons in, the next thing we would do is we would count how many electrons each of the atoms in the structure has. And we may need to rearrange the electrons on the outer atoms to make multiple bonds in order to get the central atom to have the octet, or 8 electrons, to make it stable. So how many electrons should we share between atoms? As many as we need to give a full valence. And for most atoms, that means 8 electrons, and we call that the octet rule. Now, some exceptions. Hydrogen doesn't form the octet rule. It's stable with 2 electrons. Beryllium is stable with 4 electrons, and boron is stable with 6 electrons. Now, atoms that are in the third period, the third row on the periodic table or greater, oftentimes will have more than 8 electrons as their valence electrons, and we would refer to them as being hypervalent. So let's look at some examples. If we have carbon tetrachloride, it contains 1 carbon and 4 chlorines. Each carbon has 4 valence electrons, and each chlorine has 7 valence electrons, and there are 4 chlorines. So our formula is CCl4. That gives us a total of 32 valence electrons. Next, we put carbon in the center, and then we put our 4 chlorines around that central atom. We put a lone or bonding pairs of electrons between the carbon and each of the chlorines so that they function as a unit. That's 8 out of the 32 electrons. We've got 24 electrons left, so now we start putting lone pairs of electrons on the chlorine until the chlorines are stable. Now, to kind of clean it up a little bit, instead of having a pair of dots here, we're going to substitute it with a line. So this line represents a single bond or a pair of electrons being shared between carbon and chlorine. And if we were to look, once the structure is complete, there's a total of 32 valence electrons in our carbon tetrachloride. We've got 4 single bonds, and then we've got 3 lone pairs of electrons on each carbon or chlorine. So this chlorine has 2, 4, 6, 8 electrons. The octet rule is fulfilled. This chlorine has 2, 4, 6, 8 electrons. This one has 2, 4, 6, 8. And this one has 2, 4, 6, 8. And if we were to look at carbon, it also has 2, 4, 6, 8. So this Lewis structure shows all 32 valence electrons arranged in such a way that all of the atoms in that structure have fulfilled their octet. Now, let's say we look at silane, okay? It contains silicon and 4 hydrogens. So silicon has 4 valence electrons. Each hydrogen has 1 valence electron, and there are 4 of them. So that means we've got a total of 8 valence electrons. Silicon would go in the center. Our 4 hydrogens would go around the silicon. We would put a lone pair of electrons a bonding pair of electrons between silicon and each of the hydrogens. And then that's our 8 valence electrons that we have for our structure. We'll replace the dots with a line. Again, this is going to represent a bonding pair of electrons between silicon and hydrogen. So this is 2, 4, 6, 8 electrons. That's all the valence electrons we have for the molecule. Silicon is stable with the octet rule, and hydrogen is an exception. It's stable with just 2 electrons, and we've got 2 electrons on each of our hydrogens, so this would be a stable structure. If we have ammonia, okay, ammonia has 8 valence electrons. We've got 3 bonding pairs of electrons and 1 lone pair of electrons, and that would make the structure stable. Water has 8 valence electrons. And again, the way we figured that out is oxygen has 6 valence electrons, since it's in the 6th group. Each hydrogen has 1 valence electron, and there are 2 hydrogens, so we've got a total of 8 valence electrons. Oxygen would go in the center. Each hydrogen would go on the outside. We'd have 2 4 electrons with bonds. That would leave us with 2 4 electrons, which would form our lone pairs of electrons on oxygen. If we were to look at hydrogen fluoride, it has a total of 8 valence electrons. We put fluorine and hydrogen. We have a single bond between the two, which represents a pair of electrons being shared between the 2 atoms. We have 6 electrons left over, which would be these 3 lone pairs of electrons. Hydrogen would be stable because it has 2 valence electrons. And our fluorine would be stable because it fulfills the octet rule, and it would be stable. So here are some more examples. If we were to look at, we looked at carbon tetrachloride. So look at CH2O. Carbon, because it's in the 4th group, has 4 valence electrons. Each hydrogen has 1, and there are 2 of them. So there's 2 valence electrons here. And oxygen has 6 valence electrons since it's in group 6. That gives us a total of 12 electrons. Carbon would be our central atom. We would put bonds between our carbon and each hydrogen. and a single bond between carbon and oxygen, that would be 2, 4, 6 electrons. We've got 6 left, so we would put 3 lone pairs of electrons on oxygen. But when we count everything up, carbon will not be stable unless we move a lone pair of electrons off of oxygen and make it a bonding pair of electrons between carbon and oxygen, therefore forming a double bond. So we've got 2, 4, 6, 8, 10, 12 electrons in our structure. Hydrogen is stable because it's got 2. Hydrogen here is stable because it's got 2. Carbon is stable because it's got 2, 4, 6, 8. And oxygen is stable because it's got 2, 4, 6, 8. So this would be a stable structure. Now, NO with a +1 charge is a little bit different. Nitrogen has a 5 valence electron since it's in the 5th group. Oxygen has 6 valence electrons because it's in the 6th group. And this +1 charge means that this structure has lost 1 electron. So we've got 10 total valence electrons that we need to use to make our Lewis structure. We've got nitrogen and oxygen. We would start with a single bond. That would be 2 out of the 10 electrons. We've got 8 electrons left. Oxygen is more electronegative, so we would put 2, 4, 6 valence electrons on oxygen. And then the remaining pair would go on nitrogen. But nitrogen won't be stable unless we move 2 lone pairs of electrons and make them bonding pairs of electrons between the nitrogen and the oxygen. That forms a triple bond. We've got 2, 4, 6, 8, 10 electrons in our structure. Nitrogen has a lone pair of electrons and 3 bonding pairs of electrons, so that's 8 valence electrons. The octet rule is fulfilled for nitrogen. And oxygen has a lone pair of electrons and 3 bonding pairs of electrons, so that gives us 8 valence electrons on oxygen. Oxygen is stable. But different for this structure than the other ones we've done so far is because this is an ion, we're going to put brackets around the ion and put a +1 charge. Because what that means is this structure overall has lost an electron to something else and formed a +1 charge. Let's say we've got CHO2 with a -1 charge. So carbon has 4 valence electrons. Hydrogen has 1 valence electron. Each oxygen has 6 valence electrons, and there are 2 of them. And this -1 charge means that this ion has lost an electron. So we've got 4 plus 1 plus 12 plus 1. We've got a total of 18 electrons that we need to distribute into our structure to make everything stable. Carbon will be our central atom. The atom that's the most electronegative is typically our central atom. If you see carbon in a structure, it'll be your central atom. We would put a single bond here, here, and here to bond all of our atoms together. That would leave us with 12 electrons. We would put 6 electrons here, 3 lone pairs, and 6 electrons here, 3 lone pairs. But then when we look, carbon will not be stable unless we take a lone pair of electrons off of oxygen and make it a bonding pair between oxygen and carbon, therefore forming a double bond. So we've got 2, 4, 6, 8, 10, 12, 14, 16, 18 valence electrons. That's all the electrons we have for our structure. Hydrogen is stable with 2. This oxygen is stable with 2, 4, 6, 8 electrons. Carbon is stable with 2, 4, 6, 8 electrons. And oxygen is stable with 2, 4, 6, 8 electrons. And this is a ion with a -1 charge, so we're going to put our brackets and we're going to put that minus charge, which means that this structure gained an electron from somewhere else in order to make all the atoms stable in our Lewis structure. Now let's look at ozone. Ozone has 3 oxygens. Each oxygen has 6 valence electrons. That means we've got 18 total electrons. We would put our 3 oxygens with a single bond between each. So that means we would have 14 electrons left. We would put electrons on our oxygens, but we're going to notice that we're going to have to move a lone pair of electrons off of this oxygen and make it a bonding pair in order to make all 3 of our oxygens stable. If we look at C2H2, we've got 2 carbons, each with 4 valence electrons, 2 hydrogens, each with 1 valence electron. So we've got 10 valence electrons to work with. To make our structure stable, we would put single bonds between each of the hydrogens and carbon, but we'd have to put a double bond between our 2 carbons in order to make all of our atoms stable. So each hydrogen has 2 valence electrons, and each carbon has 2, 4, 6, 8. 2, 4, 6, 8 valence electrons. Now, what does it mean to have electron deficient molecules? Sometimes we're going to see molecules that don't have a fulfilled octet. Okay, so beryllium is stable with just 4 valence electrons. So we don't fulfill the octet rule here, but this is a stable structure. Boron can be stable with just 6 valence electrons. It's an exception. Oftentimes, they're going to combine with other molecules containing lone pairs of electrons. So as an example, if we have BF3, because boron is an electron deficient molecule, it often bonds with a molecule of ammonia to make a more stable structure. Or sometimes they even form kind of strange looking molecules. We're not really going to get into these 2 examples, but we should know that beryllium is an electron deficient molecule or atom, and boron is also an electron deficient atom. Now let's look at hypervalent atoms. Okay, these are ones that can have more than 8 valence electrons. They're going to be in the 3rd row or lower. And the reason for that is once we get into the 3rd row, we're going to start to see p orbitals becoming available. And when the p orbitals are available, there's more room to expand our octet and form what are called hypervalent atoms. So hypervalence originates from the need to hold more than 4 atoms. Let's say we've got PCl5. Oop, maybe I don't have that structure there. So PCl5 exists even though there are 5 chlorines bonded to phosphorus. That means there are 5 single bonds. That would be 10 electrons around phosphorus. Or if we were to look at SF6, we've got 6 fluorines bonded to sulfur. That's a total of 12 electrons on sulfur, which is more than that typical 8 that makes an atom stable. So hypervalence originates from leftover electrons. So if we have IF5, we're going to have 5 fluorines that are bonded to each iodine. How does that happen? That's only going to happen if iodine has the ability to accept 2 more valence electrons and become hypervalent. If I were to look at xenon tetrafluoride, xenon actually already has 8 valence electrons. So in order for it to bond with other atoms, it's going to have to expand its octet. So what are radicals? When we talk about radicals, they're going to have an odd number of electrons. So they're molecules that contain an odd number of electrons called free radicals. And these molecules will always have electron deficiency in their structure. The atom in the structure that's more electropositive is the one that's going to have a lower electronegativity. It's not going to have as much of an attraction for electrons. So here's an example. If we were to look at NO, nitrogen has 5 valence electrons, oxygen has 6 valence electrons, so we have 11 valence electrons in the structure. That's an odd number. When we make that structure, we're going to notice that nitrogen is going to have 2, 4, 6, 7 electrons. It's going to be an electron deficient element. And the reason why it's nitrogen and not oxygen is because oxygen has a higher electronegativity or attraction for electrons. So it will pull the electrons towards itself and fulfill that octet rule. So if we have C2H, we would have the same kind of structure where we've got an odd number of electrons, and that odd number of electrons would be on our carbon.